Hi, my name is Dr Steve Devine and I'm the Chief Technology Officer at Graphene Composites Limited. I would like to talk to you today about a new technology Graphene Composites is bringing to the marketplace, GC Halo. GC Halo is a new, powerful ink formulation that establishes a virucidal, antimicrobial and anti-mold coating which can be deposited onto a number of surfaces. The purpose of this presentation is to go through the first application for this technology, which is virucidal filtration. The presentation I will give today was first presented at the Advanced Materials and Technology for the Medical Sector conference back in April 2022 at the Edgbaston Park Conference Centre in Birmingham. The conference provided an excellent opportunity to learn about the latest innovations, advancements and projects taking advantage of advanced materials within the medical and healthcare sectors. Graphene Composites is an innovative nanomaterials engineering company driven by an ethos to create life-changing products. As a world leader in nanomaterials research, development and design, we apply our core nanomaterials engineering expertise to a wide range of applications. We work with manufacturers to resolve key technical challenges by developing breakthrough solutions and incorporating our technologies to enhance existing product performance. Before we look at the presentation, can I bring your attention to the logo on the bottom right of the screen? We are very proud of our Mass Challenge Platinum Award from October 2020, which recognised our contribution to the initial development of the GC Halo product, as well as our innovative ballistic protection products. So without further ado, let's start the presentation. The general theme of the talk will be the rationale behind our decision to focus on the air filtration market rather than other areas such as face masks, for example. In doing this, I intend to concentrate on the design considerations for filter development rather than going into great details on the ink science. The first area to look at is why air filtration is so important and what are the challenges to producing clean air. A major part of the rationale behind the development of GC Halo was the prevalent infection mechanisms presented by the SARS-CoV-2 virus. In the presentation, we will examine the importance of these mechanisms and what physical means can we use to interrupt these infection routes. Another area we will look at is the development of GC Halo in terms of physical testing, looking at areas such as filtration efficiencies and efficacies against the various pathogens we have tested against. We will also examine the potential safety concerns and resultant mitigation strategies for our product. Finally, we will take a brief look at what the future holds for this and similar products. There are several factors which lead to a challenging situation. Firstly, we spend around 90% of our time indoors, and when you combine this with the ability for aerosols to remain airborne for several hours, the transmission of airborne aerosolized pathogens becomes very prevalent, especially during colder times. This leads to billions of dollars being lost around the world due to sick days. With increased scientific knowledge regarding viral and bacterial transmission indoors, improved air filtration and better ventilation now feature highly in public health risk reduction strategies. It is an interesting quotation from Jose Luis Jimenez, an aerosol scientist at the University of Colorado, who's quoted, "We've wasted billions and billions of dollars on disinfecting, yet things like having a $50 filter in every classroom we haven't done." So definitely food for thought there. ASHRAE, the American Society of Heating, Refrigerating and Air Conditioning Engineers, has over 57,000 members in more than 130 countries worldwide. ASHRAE are leading experts on indoor air and have developed many of the standard tests, such as filter efficiencies, used within the industry. In their initial COVID-19 response, ASHRAE concluded, "Transmission of SARS-CoV-2 through the air is sufficiently likely that airborne exposure to the virus should be controlled. Changes to building operations, including the operation of heating, ventilating and air conditioning systems, can reduce airborne exposures." So there is a general consensus that controlling ventilation and filtration is a key step in controlling the spread of disease through airborne transmission. But how is a virus like SARS-CoV-2 spread? The graphic shows a representation of a water droplet containing approximately 10 SARS-CoV-2 viral particles. If you look closely, you can see the now well-recognized protein spike structure. The image is relatively true to scale for a water droplet size of 1 to 10 microns. Exposure to respiratory fluids containing SARS-CoV-2 is how the infection is spread. There are three main routes for this. Inhalation of aerosolized respiratory droplets floating in the air. Deposition of respiratory droplets directly on exposed mucous membranes in the mouth, nose, or eye by direct spray. Or touching mucous membranes with hands which have been soiled with infected droplets. More recent studies have shown that the first two mechanisms account for over 95% of COVID-19 infections. Strategies such as social distancing and to some degree face coverings are effective against direct impingement of infected droplets. The ability of aerosolized particles to remain suspended in the room air for many hours are not so easily controlled by these strategies. How long do these particles stay in the air? The graphic shows the effective settling rates for different particle sizes. The settling distance used is 5 feet, which is an average human mouth height. These results assume no crossflow of air which could affect the particles. The size ranges of interest are below 10 microns. We can see from the graphic that sizes in the range of 3 to 10 microns remain airborne for minutes. However, below 3 microns, particles remain in the air for hours and are of course in real life susceptible to movements of air within the room, potentially prolonging this residence time. Particles below 1 micron remain in the air for 12 hours or more. The next question to ask is what size ranges of droplets are exhaled. Before we look at the actual size ranges, let's look at how the droplets are formed. Droplets exhaled through breath can reach a distance of 1.5 meters, hence why initial social distancing strategies were set at 2 meters. When we look at a person coughing, the velocity of drops can be up to 10 meters per second, and droplets can reach a distance greater than 2 meters. However, when we look at sneezing, the velocity of droplets can be up to 50 meters per second, with droplets reaching a distance in excess of 6 meters. The graphic shows the particle size distributions generated from sneezing in blue, coughing in red, and ordinary talking in green. In terms of the particle size, there are only minimal differences between the three distributions, with sneezing producing marginally smaller average particle sizes, but this is 8 microns compared to 10 microns for the other distributions. The main difference between the three distributions is the number of particles generated at any given particle size. Remembering that the vertical axis is a log scale, at 10 microns, for example, sneezing generates approximately 300,000 droplets, while coughing only produces 1,500 droplets of the same size, and talking only generates around 100 droplets. Although these processes can generate significant numbers of airborne particles, the good news is that these can easily be removed via filtration systems. I mentioned ASHRAE earlier in the presentation. They developed the MERV rating for air filters. MERV, or Minimum Efficiency Reporting Value, is a measurement scale which determines, through standard tests, the efficiency of an air filter. The higher the MERV rating, the greater the efficiency. The graph on the left shows the particle size on the horizontal axis and the fractional efficiency on the vertical axis. The graph shows efficiencies for MERV 6 through to MERV 16 ratings. The one obvious feature which stands out from this graphic is how the efficiency of all the ratings drops off between 0.1 and 1 microns. Remembering the previous size distribution graphs, there are only low percentages of droplets at this size range within the distribution. But this fall off in efficiency means that you will never get 100% filtration across the size distribution range. The graph on the right shows that there are commercial considerations in choosing a suitable MERV-rated filter for your application. Upgrading filters constructed at MERV 4 to say MERV 11 has only a modest annual cost increase. However, move above MERV 13 and the annual cost of replacement and upkeep starts to increase dramatically. For example, moving from MERV 13 to MERV 16 has a $75 increase in annual costs. Another parameter to consider is the increase in pressure drop associated with higher MERV ratings. Older or lesser rated fan and motor systems may be incapable of operating with a higher MERV rated system due to the increased workload. The rotating graphic shows the result of the Graphene Composites approach to this aerosolized droplet problem. The front of the filter shows a traditional pleated system manufactured from polypropylene filter fabric, but the back of the filter has an additional layer added to the system which is coated in the GC Halo ink. The system can be tuned to operate at any MERV rating by adjusting the materials of construction of the pleated filter material. The system shown has a MERV 8 pleated system with a MERV 7 GC Halo coated material, which gives an overall filter efficiency rating of MERV 12. There is a lower pressure drop associated with this system when compared directly to a MERV 12 system. This, we believe, is due to the velocity of droplets being reduced by the pleated filter, which increases the droplet removal efficiency of the GC Halo coated material. The active particles within the GC Halo ink are single-layer graphene oxide flakes decorated with silver nanoparticles. The upper micrograph shows the starting base material of graphene oxide, which has a typical lateral dimension of 5 to 8 microns. Our production process renders greater than 95% single-layer graphene oxide flakes. The silver nanoparticles at 10 to 20 nanometers are adhered to the oxygen, hydroxyl and carboxyl bonds around the periphery of the GO flakes. The bottom micrograph shows the spatial positioning of the silver nanoparticles. These can be seen as the small white dots on the edges of the GO flakes. The film-forming nature of this ink is also illustrated here, with GO flakes forming a single-layer engineered film, in this case on a silicon wafer for imaging. The engineered coating adheres extremely well to cellulosic-based fibers. The 4 micrographs to the right show a cotton-based material coated with GC Halo ink. The ink imparts a slight brown coloration to the product, but there are no GO agglomerates to be seen, and the engineered film, which coats the entire fiber, increases the fiber width marginally, which results on a minimal impact on the pressure drop. The other graphic shows a representation of the silver decorated GO forming a continuous film on a fiber with water droplets to scale to show how the mechanism of attract, absorb and destroy works within the system. The GC Halo ink exhibits dual-action trap-and-kill nanochemistry. The nanomaterials used in the ink, graphene oxide and silver, work synergistically to give an improved product compared to that of the individual components. After entering the filter system, water droplets adhere onto the graphene oxide surface, which then absorbs the carrier liquid, introducing the viral particles to the oxidative surface of the GO and silver. The silver nanoparticles then oxidize the protective lipid membrane of the virus or microbe, which causes the layer to rupture, releasing the contained RNA into the environment. This renders the virus inoperable as it no longer has the ability to reproduce. GC Halo is a patent-pending technology. The GC Halo ink has been extensively tested in both wet ink and dry coating scenarios. As a liquid ink, 100% virucidal efficacy versus influenza A, H1N1 and coronavirus OC43 have been recorded during testing at Brown University in the USA. In addition, as a liquid ink, minimum inhibitory concentrations have been determined against bacteria E. coli and Staphylococcus aureus, as well as black mold, Aspergillus niger, as part of our Eureka program testing. As a dry ink coating on filter fabric, testing against ISO 18184-2019, at least 99% virucidal efficacy against SARS-CoV-2 coronavirus has been recorded at VRS laboratories in the UK. In addition, with other filter media such as viscose-based materials, it is possible to achieve levels as high as 99.9% efficacy, which is log 3.5 against SARS-CoV-2. As a dry ink coating, A log 8 reduction against Staphylococcus aureus has been observed as part of the Eureka program. We have given great consideration to the potential safety issue of the graphene oxide flakes becoming airborne and as a result becoming a respiratory hazard. To avoid this scenario, we have engineered the graphene oxide to film form on the fibres and have extensively tested the product to ascertain whether this has been achieved. We built a test rig which passed high-velocity air through a filter. The air was then routed to impinge on an adhesive plate. Any particulate matter coming off the filter then sticks to the plate. Careful selection of the adhesive, we used a silicon-based adhesive as opposed to a carbon-based one, means that Raman mapping can be used to analyse any particles trapped by the adhesive without any risk of signal masking by a similar signal from the adhesive. To date, only filter fibre material has been observed. No graphene oxide has been shed, and this is a result which has also been confirmed by work carried out at George Washington University. The top right graphic shows a typical scan of the Raman mapping. The bottom right graphic shows that when the film is deliberately forced off the filter, there is no free graphene oxide observed. It remains within the film. The National Physical Laboratory tested coated and uncoated viscose and cotton fabrics to BSEN 14683-2019 Annex C to determine the pressure drops across the filter materials at different airflows. The graph shows that there is a minimal increase in pressure drop associated with the ink layer. The majority of the pressure drop is associated with the additional filter material element in the final filter system. The Biden administration recently announced the Clean Air in Buildings Challenge. One prime objective of this challenge being enhanced air filtration and cleaning using the central HVAC system and in-room air cleaning devices. We are working with the various authorities to mount a substantive program to meet this challenge. To complete this, though, it is necessary to navigate through the maze of legislative requirements as the ink layer is categorised as a pesticide to the EPA. In parallel with this, we are looking to branch out into the Southeast Asian and African markets with air filter systems for car cabins and buildings. So thanks for watching the video. If there's any more information that you require, please don't hesitate to get in touch with me at steve.devine@graphenecomposites.com, or there is a lot more information on our website at www.graphenecomposites.com. Thank you now. Bye.